going to talk about elliptic integrable models and their spectra from superconformal indices.
I would like to thank organizers for bringing all of us here and organizing this great conference and for giving me an opportunity to present here. So I will continue talking about one of the topics which Shlomo touched upon in his talk, and this is a relation between integrable. Oh, okay, let me put it here maybe. Okay, hopefully it won't fall. About the relation between some integrability and superconformal indices. Okay, actually somehow my slides are a bit cut off on the left, but okay, hope it won't affect, I don't know. Is it full screen or presentation mode? Maybe you should download and yeah. Yeah, it's still not what. Yeah, great. Thank you very much. Okay, coming back. We'll talk about relation between some integrable structures and indices, and that's something we were working with Shlomo for some years already. And there are some other people involved, in particular Hicheol Kim from Posttech Korea and Bilal Nazal, who was PhD student of Shlomo. Okay, so the main idea here is in the realm of what is people refer to as BPS-CFT correspondence, which was started by Nekrasov and Shitashvili. Sometimes it's also referred to as beta gauge correspondence. The main idea is that when you have supersymmetric field theory, sometimes when you compute some protected observable in these theories, you find out empirically that it is related to one or another integrable structure. So this is a very general setting. We will be talking about something more particular here. This is our particular setting. We'll be talking about compactifications of six-dimensional superconformal field theories down to 4D QFTs on some Riemann surfaces. Then we will be also introducing codimension 2, so surface defect in 4D. And as people noticed, this often leads to some relation to some integrable and elliptic finite difference operators. Why is this important? Shlomo talked about this a little bit already. This allowed people to compute indices even of theories which have no Lagrangian description. It was the first emergence of this setting was in this paper by Shlomo together with Gaiotto and Rastelli, and it appeared in the context of computing compactifications of six-dimensional 2,0, the favorite theory in 6D of many people, which led to class S theories in 4D. And on the dual side, a Ruchiner-Schneider model which appeared, which was known by a mathematician, and that allowed people to compute some of the indices of non-Lagrangian theories. So this is our setting. I won't be talking much about compactifications here because Shlomo already talked a lot about it. I will just refer you to his talk. But the setting is the same. So we start with some six-dimensional superconformal field theory. We put it on a Riemann surface with some punctures, with some genus and flux of global symmetry. And this triggers RG flow across dimensions. We land on some four-dimensional supersymmetric field theory in IR, which can happen sometimes to have another UV completion inside 4D. In this case, there is Lagrangian description. Otherwise, there is no. Okay. As I told you, I won't be giving you much about 6D compactifications, but I would remind you something that Shlomo talked about. What is punctures? This is central object for our constructions. Punctures in our constructions are considered as just some objects coming with globals together with some global symmetry and bunch of operators charged under subgroups of this global symmetry. For this super simplistic picture of puncture, we need 6D theory to have gauge description for 5D circle reduction. This is also something Shlomo touched upon in his talk. And we can do some operations with this puncture. One of them is gluing. So Shlomo discussed cutting. I will discuss gluing. It's opposite operation. So we take two Riemann surfaces with some puncture, and we can glue along this puncture them back together. So on the field theory side, what you do for this, since you have punctures, you have this set of operators in global symmetry. Operators on two sides should be identified, meaning that we identify their charges. Practically, this is done by introducing some superpotential, which does the job for you. And then we need to gauge the global symmetry of the puncture. Okay, this is gluing, and another procedure is closing. So if we have the puncture, we can close it. And we close the puncture by breaking global symmetry, which corresponds to this puncture. So if the global symmetry is broken completely, puncture is closed completely. So there is no more puncture. How you break global symmetries? You give veps to some operators which are charged under these global symmetries. Fortunately, puncture is already equipped with such set of operators, but we can also give veps not as we usually do to operators themselves, but to their derivatives. So we are in 4D, we can define two holomorphic derivatives and give vep to these derivatives. And in this case, we will have surface defects, as I will discuss later. So the main object we consider is superconformal index. This is general slide. Many of you, I'm sure, are already familiar. So we basically, if we have some supersymmetric impact theory, we can put it on S3 cross R and do radial quantization and compute certain trace of this form. We introduce some things we call fugacities, this QP and UIs. And fugacities are bookkeeping things to understand what are the charges of certain operators we count. And the global symmetries I write here, it is like spin 4, so Lorentz symmetry, some U1R symmetry, which is common for all supersymmetric series, and then there are some specific global symmetries. In our setting, global symmetries has two sources. One source is the part of the global symmetry that survives when we compactify from 6D, and part the one which is brought by the punctures. And we know how to compute these indices. They are like well-developed technology using localization or some UV computations because index is RG invariant. We can reduce this to some matrix integral and then try to compute this matrix integral. So for indices, we can define also all these punctures operations which I talked about. One is gluing, this is defined here. So basically, you take indices of the compactifications on two Riemann surfaces, the colors corresponding to the surfaces, and then you need gauge global symmetry corresponding to the puncture. So gauging here is basically integration over the fugacity of this puncture, of this global symmetry of the puncture. Integration that basically projects out states on the gauge singlets, onto gauge singlets, and also we need to add some integration measure which physically is given by contribution of some multiplet. At least vector multiplet is always there. This is n equal 1 vector multiplet, index of n equal 1 vector multiplet, but in principle, depending on some details of the gluing, you can have other multiplets. Closing puncture is a little bit more complicated. So basically, assume that you have some puncture with the minimal symmetry, U1, and you have some operator charged with charge -1 without loss of generality under this U1, then this is the contribution to the index. This is basically what stands under the trace. And it appears that the index in this case, it has certain poles positioned at these values. Values U equal this capital U times some PM QM. And these poles actually, if we give VEF to these derivatives of this operator with powers m and n, this triggers RG flow. And the theory flows somewhere, and if we compute index in infrared, we need to just compute the residue in one of these poles, which in UV index have. So this m and n are non-negative integers. If they are 1, if they are 0, we just derive back to UV index, nothing happens. Just this U disappears. But if the M and N are M and or N are non-zero, we physically introduced codimension 2 defect. In this paper by Gade and Gukov, it was checked by direct computation of 2D 4D system and comparison with the index of 2D 4D system and comparison with this residue computation. Okay, now let me move to the operators. So we have two working conditions which we use to derive these operators from indices. That we have a circle reduction, which is gauge theory, and that 4D trinion is Lagrangian theory. So trinion is compactification on a 3-puncture sphere. What is the idea of how we introduce defects and derive our operators? So we start with some compactification with certain puncture u. We introduce extra minimal puncture. We use it using trinion, in fact. That's why we need Lagrangian description for the trinion. We introduce this extra minimal puncture. Minimal puncture is puncture with SU2 symmetry, or U1, minimal symmetry you can have. And then we close it, but with this space-time dependent VEF. So in principle, we arrive back to the same Riemann surface, same compactification. But now we have also introduced defect into this theory, which corresponds to this compactification. Then we run all this this is graphical representation of the computation. We run this computation on the indices, and we arrive to this formula that the index of the theory with the defect, which is this one, equals some operator, finite difference operator, labeled by m and n. M and n is basically number of the derivatives we have in the VEF, acting on the original index of the theory. So, and we obtain actually, in fact, infinite tower of operators immediately. Okay, and these are our operators, which often happens to be integrable. There are two important properties that come for free with these operators. They follow from S-duality, actually. So the first one is commutativity of operators. So all of these operators commute with each other. I here dropped m and n the indices and substituted them with single index for compactness of notations. So all of this tower of operators commute with each other. This follows from S-duality. Basically, you can see it as a fact that if we have two minimal punctures, it doesn't matter in which order we close them. And different order of closing corresponds to different order of operation action. And it says duality because you can also see it as putting these punctures in different positions, which is basically action of S-duality on this Riemann surface for the S-duality. So this is one property, and it signals integrability. It's only a signal. Of course, in each case, it should be proven. But in those cases in which operators you obtain in this construction are known by mathematicians, they were integrable, actually. Second property is even more important for us, and it's a kernel property of operator. This is something maybe you don't know what it is. So what is kernel property? What is kernel function? So kernel function is a function related to some kind of operator that depends on several variables. And if we act with this operator on one of the variables, like I write here, and so this lower index of operator is which variable it acts on, and we act on another variable, then we get the same result. And we can have many variables, more than two. And this also follows from 4DS duality, because we can again see it as our results of computation being independent on where our minimal puncture is on the surface when we close it. If it's close to this puncture, then we will obtain operator acting on this puncture. If it's close to another puncture, we will obtain operator acting on another puncture. Why this property is important? Assume we know the spectrum of our operators. So we know the spectrum. There is this label lambda, which labels the eigenvalues and eigenfunctions. It can be integer. It can be partition, like in many, many cases. And we also choose these eigenfunctions being naturally orthogonal under our gluing measure delta, which I introduced previously. So if we know the spectrum, then there is a natural ansatz for kernel functions, which mathematicians use. And this is what Shlomo exactly showed you when he was showing index of general theory. Basically, the thing is that this is expansion in the basis of eigenfunctions, but it's diagonal expansion. So we have just single sum instead of many sums. Here I write, for example, compactification on a surface with S punctures of the same type, these coefficients, their structure depends on the details of compactifications like genus, flux, all these things. So what I will also do, I will say that we assume that this label lambda has some natural ordering, and using this natural ordering, I will rewrite the sum just as a sum over integers. Here, as an example, I give you the surface with the two punctures. It has this super simple structure. Of course, we don't know these C lambdas, which makes our life a bit more complicated. So this allowed people, in principle, to write indices of even non-Lagrangian theories, which is a great achievement. But we asked ourselves with Shlomo, like, can we revert this game and instead of defining spectrum from the indices, indices from the spectrum, define spectrum from the indices, because often it happens to be that spectra of these operators, they are not known, actually. Okay, and that's with the game we played. And to play this game, we need basically more or less only one thing. We need some Riemann compactification on a Riemann surface, which should have Lagrangian description, so we can write its index, not in this form, but in precise form. But also it should have either some non-trivial genus or some non-trivial flux for the things to work. So then it has this expansion in terms of eigenfunctions, which we don't know originally. So we don't know these eigenfunctions, but we can formally write this expression. Then we start gluing them together many, many, many times. After each gluing, we still end up with a surface with two punctures, but we have more genus and more flux. So what happens with the expansion? This happens with the expansion. You still have these two eigenfunctions, but your coefficients start having power n. Now we will play the game usual for the index. We will expand it, consider the expansion in this parameter pq, which corresponds to the fugacity counting the R charge of the operators. So this is the typical expansion for the index, and we assume this product pq is less than 1. And another assumption, bold assumption we make is that these coefficients C lambda, they are ordered. So meaning that the lowest non-vanishing order in expansion in this y equal pq increases with the increase of this index I. We don't have justification for this assumption, but we check our construction for consistency. So meaning that when we do computation, and the end of computation, we check that this holds. So now, since we have this expansion and this assumption, let's say that we take n to infinity. We glue infinite number of these two punctured spheres. Then what happens is that out of this sum, only the first term, ground state contribution, will survive. It's something, if you want to think in a simple terms, what you do in thermodynamics in zero temperature limit. You also take some infinite limit, and only the ground state survives. So here it's something similar happens. And in this case, we can compute this C lambda 0 as this ratio of indices n plus 1 and n and limit n to infinity. Substitute this C back to here, which now has only one term survived, and compute the ground state wave function. Of course, you have here limit n to infinity, meaning you need to glue together infinite number of surfaces. This is, of course, practically not doable. But what you can practically do, you can glue many of them. I think we were going up to 20. And then your result of computation will be valid up to certain fixed order in expansion you do. So that's what we do practically. And then you can repeat the procedure, subtracting contributions you already calculated and doing it for higher and higher terms. So knowing ground state, you can derive first excited state, second excited state, and so on. Okay, so far everything was abstract. Let me give you some examples. So an example is the most basic one, Ruchiner-Schneider model, which is known since forever. So it emerges in the compactification, as I told already, of 6D2,0 theory down to class S. Circle compactification is maximally supersymmetric Yang-Mills, so it works. And I remind you, these are two working assumptions for our operators to be derived. Trinian theory is just bifundamental. So then we derive operators. In general, we get an Ruchiner-Schneider if we start with an type 2, 0. Here I write Hamiltonian for A1. For an, you will get n Hamiltonians, which will be very complicated, but this is to give you ideas how this integrable models looks like. We have some theta functions and some shift operators. So now, what's known about the spectrum of this operator? In general case, explicit form of the eigenfunctions is not known. But what is known is this p to 0 limit, which is called Macdonald limit, where eigenfunctions take the form of polynomials and many things can be computed. And it was used a lot to compute this indices of non-Lagrangian theories. But in this limit, of course. So general form is not yet known. So let's try. So then we run our algorithm, which I presented to you previously. So two-punctured sphere with a flux is known. It's again bifundamental hypermultiplet given by this. So here I will consider A1 for simplicity. Gluing measure is just contribution of n equal to vector multiplet. Also quite simple. So then we run our algorithm doing gluing and so on. And we arrive to some sort of expressions for these eigenfunctions as a series in PQ expansion. So these are orders up to which we manage to expand. So parameter of expansion is basically square root of PQ. Actually, it's PQ powers 1/4. So this is pretty high order of expansion. The technical problem here is that when you go to higher orders, this order up to which you can successfully expand drops. So if you see, if we expand here up to 7/2, here we get 3/2. But in principle, okay, here, for example, we didn't manage to go further than first excited state so far, but at least ground state and first excited state are derived. Then we substitute it back to our eigenfunction equation, and we get both the cross-check that we derived our eigenfunctions correctly, and also we get the eigenvalues also. Now the question, what do we compare this for to check like what's going on? One thing, of course, we checked all the possible limits, like Macdonald limit, which I mentioned before. But there is actually one approach, which is unfortunately not very widely known, but there is another approach for the spectra of these integrable models. And it's given by ramified instanton calculations, introduced here in this paper. So setting here is different. Now we live in 5D instead of 4D. The theory, if we consider Ruchiner-Schneider, is n equal 1 star, which means this massive deformation of maximally supersymmetric Yang-Mills, and we put it in omega background. Then we introduce again surface defect of Gukov-Witten type, which breaks our gauge symmetry down to Levy subgroup. We labeled by this partition. So, and we compute the index Nekrasov partition function for this supersymmetric theory with a defect introduced. So I won't write expressions, they're huge, horrible, and so on, and won't give you much information, but these are parameters which it depends on. So we have instanton parameter in 5D. We have instanton parameter in each of the subgroup. After it's broken, we have mass of the adjoint hyper and Coulomb branch parameters. And I also introduce Q and T, which are exponentiated equivariant parameter and mass parameter. The names Q and T are not accident. It's same Q and T you had before in terms of Ruchiner-Schneider. And we take Nekrasov-Shetashvili limit. One of the equivariant parameters goes to 0. It's singular limit. We need to regularize it. We do all the tricks. And now, okay, now let's go to the simplest case of A1, where we have SU2 super Yang-Mills. Introduce this defect which breaks SU2 down to 2 U1s. These are two instanton parameters. This will be our coordinates of Ruchiner-Schneider model. And indeed, we can show that the Nekrasov-Shetashvili limit of this instanton partition function is a formal eigenfunction of Ruchiner-Schneider. If we identify instanton parameter Q with this P we had before, then we have this eigenvalue equation. The problem, there are two problems here. Oh, yeah, an eigenvalue actually here has physical meaning as a Wilson loop expectation value in this 5D theory. That's a kind of cool, because this is even easier to compute than the instanton partition function itself. There are two problems here. That, first of all, it's formal eigenfunction, because in general, for general value parameters mu and it's not square integrable, which is not good for the spectrum. And second problem, which is actually the same problem to be fair, is that there are these Coulomb branch parameters which are not parameters of Ruchiner-Schneider. But that means that we can fix them to something and solve the problem with square integrability. And this is called Coulomb branch quantization. It was done in this very nice paper which solved some other problems I don't touch upon in the instanton computations. They proposed two quantization conditions related to bias duality of transformation of parameters. The A model quantization, where your Coulomb branch parameters solve B-transit equations. They are very complicated. They suffer from instanton corrections. This is hard. And B model, which is much simpler, where you just fix Coulomb branch parameters to certain values, and you don't need to suffer from instantons. So this n is basically a label of your eigenvalue and eigenfunction, because in case of A1, your spectrum is labeled by integer. What we did, we compared both eigenvalues and eigenfunctions of ours obtained in our computations with what you get here. So both expressions are actually perturbative and P and Q parameters. So in a sense, they live on the same footing. And in this paper with Hichiol and Shlomo, we managed to match them, kind of giving support to both our computations and to also this quantization condition fixing. Because these people, they only compared things numerically and only for eigenvalues. And the last thing I wanted to show you, I was always concentrating, giving example, I was always concentrating on this A1 Ruchiner-Schneider. So what we also did, so for Ruchiner-Schneider, we did also A1 and A2 types, and we derived ground and first excited state, and in both cases we compared it against instanton calculations. But there are other compactifications of 6D, some of them mentioned by Shlomo in his talk. For example, there is E-string theory, which leads to BC1 Van Dijk model. And this is like 8-parameter deformation in the sense of Ruchiner-Schneider. Index computation here was done by us, and we derived ground state, but for certain values of parameters, because model has so many parameters, it's hard to do in general, but we are working on it. From instanton sides, there are some computations for formal eigenfunction, which they don't call like that, but it is. But there is no quantization condition. Then there are 6D minimal, so-called minimal CFTs, which don't have global symmetries. They give rise to very nice models defined on A2 and A3 root systems. They don't generalize to higher ranks, so they are kind of isolated points. Here we did computations for the spectrum from the index point of view, but literally nothing is known so far for instantons, and we are working on it. And there are some other models which we derived with Shlomo and with his student Bilal, coming from compactifications of minimal D-type conformal matter. Here we didn't work yet on the spectrum because models are complicated, but in principle this is a long-term plan. And I will leave you with a conclusion slide. And thank you for your attention.
Thanks a lot for a nice talk. Questions? Yes.
In slide 11.
Slide 11, okay.
I'm just confused whether the wave functions are normalizable.
Normalizable? Yes, they are normal. They are normal with respect to this measure. So they are normalizable like that. Where is it? Just a second. No, here. Yeah, they're normalizable like that with this measure delta given by a vector multiplet of n equal 2.
Yeah, another question. The wave functions, are they wave functions of an auxiliary quantum system not related to the original SQFT, or is this quantum system directly related to the original quantum field theory whose index you're trying to calculate?
Original, you mean 6D?
Yes.
Well, this 4D theory comes from 6D compactification. In this sense, it's related, but maybe you want.
But here,
Hamiltonian is here, yeah. Sorry, you ask if the eigenfunction is related.
Yeah, if the eigenfunction...
Well, only in only in this sense, like that you can expand the index in terms of eigenfunctions, and you can do the opposite, which we do here. In this sense, they're related, but actually there is another relation, fairly speaking, because in instanton calculations, so you see, this instanton calculations in a sense is similar story, because what is this 5D maximal supersymmetric Young-Mills? It's circle compactification of the same 6D theory we have. And what we get here when we do calculations, as I told you, is the formal eigenfunction of this Hamiltonian. So in this sense, it's related. So in a sense, this eigenfunction is the ramified instanton partition function of circle compactification. If you want, this is the connection. Through the index, it's related in a more complicated way, which I described you here. So it's not directly related, not explicitly related. Explicit relation you can think of through 5D instanton story.
Maybe I can follow up this, because you gave a construction of the H's through the compactification, but can you make it more precise to say, given a theory, what is this operator H beyond?
Given theory in where? In 4D or?
Wherever you want to start. Because you gave a construction of the eigenvalues and the eigenfunctions.
Right.
But what is that operator in terms of QFT data? Beyond the abstract construction that you gave here. Can you have a field theoretic
Construction operation. Well, in the end, it is field theoretic, but guided by the intuition from 6D, right? Because in principle, when I was constructing it, of course, I was relying on this intuition that, yeah, we do this, this, and this. But in the end, all calculations are done inside 4D compute.
Let's say you stay in 4D, and let's say you pick the example that you had.
Yeah, I would say so. I will never guess this computation without 6D intuition, but in principle, computation is in 4D. But if your theory in 4D is not from 6D, I don't think it will work. That's the problem.
But suppose you have an example of which is kind of from 6D.
Yeah.
You know which theory you land on.
Yeah.
And you know it's still content. Maybe
Yeah.
it doesn't have a Lagrangian, but okay, you know it's still content. Can you write it in terms of, as an operator, in terms of the still content of the lower dimensional theory?
Okay. Okay, I see what you want. You are basically saying, let's solve the following problem. I give you information about just 4D theory without 6D reference, and no, that I don't think is doable. I'm not sure. I don't think it's doable. I don't know. You need some things for this thing. We don't even know the following question. We're actually trying to ask the question is like, can we surpass this 5D step? Because as I told you, the working assumption, sorry, where is it? Oh, okay, here. One of the working assumptions is that there is this 5D circle compactification. We even rely on this. We were thinking first, as a first step, if we can work around this assumption, working assumption.
But ultimately, these are properties of the four-dimensional theory.
Ultimately, yes, but probably only of those which come from 6D.
Yeah, but okay, you choose one of those.
Yeah.
So in principle, there should be some intrinsic definition of this operator.
We definitely don't have it, and I'm not sure I can Yeah, I don't know.
Yeah, well,
We don't have,
the
answer is we don't have it.
Okay.
The question, can we have it? I'm not sure I can give you the answer. Maybe, yeah, but I'm not sure.
But if in principle you cannot get it, it's not a property of 4D theory. It requires some additional structure. Because here it seems you got it via higher dimensions, which is completely fine. You're using the web of dualities that Slomo and you described today. But if it is a property of a four-dimensional theory, it should have intrinsic four-dimensional description.
No, everything here is four-dimensional. Just forget about these Riemann surfaces. Think of punctures as some global symmetries, right? And then you can do this calculation. There is some analytic structure of 4D index which has some residues, some poles and residues, and you compute these poles and residues and you arrive to this Hamiltonian. If you want, this is the answer. But it only will work for those theories which come from 6D. Yeah. I would say that, yeah, you can, looking on analytic structure of the index, probably you can derive it. One more thing I want to say. This is empiric observation. This is not some kind of proof. Just in case by case, we always get some operator. But this is empiric. In principle, it's not even clear that it always works, even if you have 6D description.
Yeah, thank you.
Okay, let's thank the speaker again for a nice talk. And